All right. What does the fundamental theorem of calculus tell us? What is the fundamental theorem of calculus?
That's like b minus a equals something.
F of b minus f of a, yes. What it tells us is if we have a continuous function and it's differentiable throughout the entire domain, then we can find that integral if we know the antiderivative of the function. In other words, what it says is this. In the domain a to b, if a function is continuous and differentiable through every place in there, in other words, the derivative exists in every place in there, in that domain. As long as we know the antiderivative of this function, what is the antiderivative? It's, if I give you the derivative, where did that derivative come from? That's the antiderivative. It's the derivative before it became a derivative. It's the original function. If we can figure that out, then we can figure out the integral. We can find the area under the curve, the rate of change occurred between there. So that's what the fundamental theorem of calculus tells us. We have two types that we talked about so far of, we have indefinite versus definite integrals. What's the difference? What's the difference?
Definite means that's like x going to infinity.
Yes. Because there's no bound, yes. Indefinite means there's no bound. So, as opposed, you're right, then a definite integral has a bound for a restricted domain. So the answer, the difference comes in, what do they give us as an answer? So what do they give us as an answer? Very good. Yes. What the indefinite does is we'll get an integral, but we'll also have a constant. It's just give us a general formula for it. Until we have a condition that we can define what the initial value is, c, this just gives us an equation. The definite integral gives us a number because since we have the function, we have to plug in the beginning and the end points and just gives us the final answer after that. So how do we find the antiderivative? We're going to look at first substitutions. Basically, as the book, as the notes say, it's running the chain rule backwards. So you know my next question is going to be, what's the chain rule? Well, all of these deal with derivatives.
It's like the square, like it was like square root of x plus 1. We like the front, you check with the parentheses, and take the outside, and then the outside derivative.
Very good. Yes. So if I give you a function that looks like this, 2x plus 3 to the power 4. Because here we have a function within a function. We have composite functions. Whenever you have a composite function, that means you have to take the derivative, the integral of both, or the derivative of both the inside and the outside. So the derivative of this one, the chain rule, tells us let's take the derivative of the outside first. So it's 4 minus 1. So remember, the power comes down first and subtract 1. Then we take the derivative of the inside. So in this case, the answer is going to be 8, 2x plus 3 to the power 3. So there's the derivative. What we're going to do now is we're going to take this equation and figure out where it came from. That's what we're going to do. Okay. So for this first example, before we get to the examples in the lecture, since we know where this one came from, let's try to take this one and try to come up with this. Let's see if we can do it. So here's our small example. The integral of 8 2x plus 3 to the power 3 dx. It's an indefinite integral because we don't know the bounds yet. Here's the basic rule, because if this was our function, where u is a function in itself, raised to a power n. The chain rule says take the derivative of the outside times the derivative of the inside. That's what we just did. This gives us our derivative. So what we have to do is we have to go backwards. So if I give you integrals. I'm going to go backwards. I'm going to start with this one. And I'm going to go backward. How do we do that? In the derivative, what do? We took the power down and we did what to the exponent? So now we do the opposite. What we do now is we add 1 to the top. But if this was 8 and we take a derivative of it, well, there's no more 8 here. How do we get rid of that 8? Whatever the exponent is, we do the same thing as the denominator. Whatever the numerator is, it goes on the bottom also. So let's do an easy one first. So if we had x to the third, what would the integral of that one be? Very good. Plus c, since it's an indefinite integral. Yeah, so we took the exponent, added 1 to it. That's where we got the 4. And then whatever that was goes on the bottom. Always check your answers. How would you check your answer? Take a derivative of this. If this is your function, if f of x equals x to the 4 over 4 plus some constant, what's the derivative? So the 4 comes down. So it's 4 minus 1. The derivative of a constant, 0. The 4's cancel, so we have x cubed. And that's exactly what we should end up with. Because remember, you start off with a derivative and you come back to the original function. Now, what we have to look for is when the equation is u. So that is our u. It's actually u of x. What is our du? Because we have to get du. What's the derivative of this one? So it's, yeah, so our u function is 2x plus 3. Our du is 2 dx. Because it's a derivative of a function with respect to x. So in our equation, since that's u, it's to the power 3. So we have u cubed. So we have u cubed. Well, we only have a 2. What are we missing here? We're supposed to have an 8, but we only have a 2. So how do we get a 4 in there? Well, we'll get, yes, but multiply by 4 actually. But but okay, so we have du. Let's take the integral of this one. The integral of x of u to the cubed is what? And then our du, we have a 2 in here. We have to divide by, because we're supposed to get 8. So we divide by 2. Because if you think 4 times 2 is, so now we have u to the 4th over 4 times 1/2 du, which makes it u to the 4th over 8 du. So remember, our original equation we started off with was 8. So we plug everything back. So we have 8 2x plus 3 to the power of 3 dx. And that's where this part goes in. So we have 8, 2x plus 3 cubed divided by 8. Not 4, I'm sorry. Because it's the fourth power. So the 8's cancel. And we have our integral. Which is exactly what our function started off as being, 2x plus 3 to the fourth. So that is what our entire purpose is, what we have to do. What we have to do is this. We have to set up our equation so that this is true. We have to set it up to resemble this function, u to the power n du dx dx. Where this one now becomes u n plus 1 over n plus 1 plus c. This is the formula we'll be using for all our examples. Example 1. Yes.
I'm so confused on why you multiply it by 1/2 and third is 2.
Because, okay, when we took, where's that one? Here. We wanted to be u cubed du, right? When we took the derivative of this, our du was 2x. But doesn't have a 2 there in front of that one. So all we have in here is dx, right? So if we were to take this one, if we were to solve for dx, what do we get? We have du over 2 equals dx. So this dx is translated into du over 2. Because when I took the derivative of it, I get that. I needed that coefficient. Because whenever you add something, you have to divide by it to get rid of it. Because it has to be equal to 1. Let's look at some of these examples. Example 1. Integrate this one. X cubed plus x, all that to the 5th. 3x squared plus 1 dx. So what would our u be? The u has to be inside the parentheses. It's usually safer because remember, you also have to find du. When you take the derivative, you always decrease by 1. So obviously, the one you look for the u part will be the higher exponent. So we're going to say that x cubed plus x is our u. All right, let's test it. What's du going to be? 3x squared plus 1. Well, that's exactly what that is. Because remember, du is a function of x. Pretty smooth. So what we have here, this is our u to the 5th, and this is our du. So the integral is going to be what? Integral goes backwards. Remember, integral goes backwards, so we add one. So what that means, now we go back, u is equal to x cubed plus x to the sixth divided by 6 plus c. So there's our answer. See, I told you, it's not difficult. It's just now we have to get our brains to work backwards. That's the hard part. And that's why this is where this semester ends up. Calculus 2 picks up from this part. When we start Calculus 2 in the summer or the fall, we'll start off using these last two sections as a review, and then we'll move on from there to the more difficult stuff. Well, the newer stuff. But it's always difficult with new stuff. All right, let's look at example 2. Well, we don't know anything further because we have no bounds. These are all indefinite integrals. The du was 3x squared plus 1. So all this part here was our du. So this is u to the fifth, and this is du. So now once we have in this format, we can take the integral of it. Add 1 and divide by that. Are you wanting more work to do? It's just that simple. If it works out like this, if it's really nice and neat, it's that straightforward. The radical of 2x plus 1 dx. Okay. What's our substitution going to be here? What's our u going to be? Then our du will be, there'll be 2 dx. Because remember, u is a function of x. So when we take the derivative of u, we have to take it to dx at the end of it. All right, so let's set this one up. How would we represent this with our u du part? So we have, let's just do, we'll do it step by step. Now, do we have our 2 dx? Do we have a 2 here? No, so we can put a 2 there. If we put a 2 there, we got to put a 1/2 there. Because the 2 divided by 2 is what? 1. It doesn't change anything. It's just we needed this format because we need to have a du has to be 2 dx. So we have to put a 2 in there, and that means whatever we put inside there, we have to do the opposite on the outside, the reciprocal. So now we have square root of u du. And there's a 1/2 out in front. The reason we put it out in front is it doesn't have a value of x or u, so it's just a constant. Now, as you said earlier, we take the radical, make it into an exponent, and integrate that. What's the integral of u to the power 1/2? Remember the formula, u to the n du is un plus 1 over n plus 1. So we have our u is u to the power 1/2 plus 1 divided by 1/2 plus 1. All that plus c. Because you can't forget the plus, put the plus c at the end of it, since it's an indefinite integral. One half plus 1 is 3/2 divided by 3 over 2. Actually, you can really don't have to put the plus c in there until the very end, if it's easier for you, because it's a lot of extra writing. Because it doesn't include anything at all. So what do we do now? Let's simplify it. So we have the 1/2 out in front. We have to multiply by the reciprocal of the bottom, which is 2 over 3, times u to the power 3/2. Simplify. The 2's cancel, so we have 1 over 3 u 3/2. 3 over 2 is an improper fraction. 1 and 1/2. Yes. So what does that mean when the whole scheme of things? It means u to the power 1, u to the power 1/2. Which is u times the square root of u over 3 plus c. And then now we have to always end up putting, what is our u? U is 2x plus 1. So our final answer is 2x plus 1 times the square root of 2x plus 1 over 3 plus c. Yeah, and that's what this section is, just a whole bunch of examples of the different scenarios. All right, let's define the substitution rule. Theorem 6. The substitution rule. If u equals a function g of x, and it is a differentiable function, whose range is an interval I, and f is a continuous function on that same interval, then the integral of the compound function f g of x times g prime of x dx is equal to f of u du. The next example. It's very important to see the connections between these two. So we usually take the internal function as our u. So if we define u as g of x, then we have f of u. Then we have to find the derivative of u, which is g prime of x. That's du. Du dx, actually. So if that works, then we could just use the integral of it, the u n plus 1 over n plus 1 plus c. Example 3. Find the integral of secant squared 5x plus 1 times 5 dx. So here are our steps. First step. Find u. So what's our u going to be here? Five x plus 1. Find du. What's du going to be? Just going to be 5. 5 actually dx. What's that? Which, yeah, which is surprise, surprise, surprise. So what we can have now is now substituted in there. So we have secant squared u du. Once we can do this, it's much easier. Now all we have to do is look at our cheat sheets or charts and see what's the integral of secant squared. Yeah, tangent of u plus c. Notice, we can only do that if our equation is set up so it matches perfectly. If this 5 wasn't there, we'd have to put a 5 there and divide by 1/5 in front. So what, because we needed a 5 for the in front of the dx. If that 5 wasn't there in the original equation, we have to put a 5 there. And since we put it in there ourselves, or if it was a 1/2, if it was a 1/2 here, what do we put in front? 2, a reciprocal of it, right? Because we want those two cancel out, but we want the setup to be perfect. So our answer is going to be what? What is u? And there you go. The way we used to have to do it in the old days before we got the big book is we'd have to go through all the trig identities and do derivatives of the 6 trig functions till we found secant squared. And we knew that's since the derivative of tangent was secant squared, the integral of secant squared is tangent. You guys are lucky. Example 4. The integral of cosine 7 theta plus 3 d theta. Following our steps. What is u? Good. So what's du? D theta. Since this is in d theta. But you're right, it's whatever the operation is, yeah. So now we substitute. So we have cosine of u. Uh-oh. We have to put a 7 there because we need that. And then we have to put a 1/7 in front. So now we have du. So we have the 1/7 out in front. What's the integral of cosine? See, you don't need that because all you need is a unit circle. We have sine up here, cosine, negative sine, negative cosine. Yeah, so the derivatives, integrals go this way. So the answer is sine u plus c. So we could just replace these. Sine 7 theta plus 3 plus c. Example 5. Sometimes we observe that a power of x appears in the integrand that is 1 less than the power appearing in the argument of the function we want. This observation immediately suggests we try a substitution of a higher power of x. Where's the example? No, this is what's saying here is this, is we had the integral of x squared e to the power x cubed dx. So which one of these two x's is going to be our du? I mean. It's going to be the higher one. Why would it be the higher exponent? Well, when you take the derivative of it, what happens? You subtract 1. So the du is always smaller than the u. Well, not always, but 99% of the time. So what we have here, we have e to the power u, we have x squared dx. That's supposed to be dx. What's missing? We're missing the 3, so we need a 3 there. So we have to put a 1/3 out in front. So now we have EU This is du. What's the integral of EU du? Remember, the derivative of EU, if this is our function, the derivative is EU du. So the integral is simply EU. So it's 1/3 e to the power x to the third plus c. And there's your answer. So far, so good. So as we talked about earlier in the examples, is that if you have x's in places, then usually the u part will be the x with a higher degree. Example 6. The integral of x 2x plus 1 dx. This example is showing what it, okay, if we had a number there, that'd be easy. If we had a number here, that'd be a lot easier. But now that we have an x, it's a little bit more of a difficult issue. What we have to do there, if we have this, an x in there somewhere, we have to rewrite x as a function of u. So what is our u in this example? 2x plus 1. What's our du? 2 dx. So since we have this x, we can rewrite this thing so far as square root of u. That's that one. We need a 2 in front of the dx. So we have to put a 2 there. That means you have to put a 1/2 out in front. So now we have du. But what about this x? What we have to do is the only place we have an x in our substitution is this one. Solve for x. Because if you solve for x, it's going to be a function of u, which is what we want in the first place. So we have u equals 2x plus 1. Subtract 1 from both sides. And then divide by 2. So anywhere we see an x, we put a u minus 1 over 2. So this x becomes 1/2 u minus 1 over 2 times the square root of u du. So far, so good. Okay, what can we do here? What would you do next? Can we take anything out of there? Are there any constants? Which one? Yeah, the half. I can bring that out in front. So we have 1/2 times 1/2 u minus 1 u to the 1/2 power. We can multiply these together, so it's 1/4 What about inside there? What would you do next? Distribute. We have u to the power 1/2 minus u to the power 1/2 du. Why did we do that? I'll show you. What is u times u to the power 1/2? This is u to the power 1. If you have the same basis, what do you do with the exponents? Add them. So that's u to the power 3/2 minus u to the power 1/2. There's a property that we can split these up and take them individually. Because now they're smaller. And usually when you have no trig functions, it's just all algebraics, and you have a monomial denominator, split them up, see what happens there. It's much easier to work with. So now we do the integrals of both of these. We do the integral of u to the power 3/2 du minus the integral of u to the power 1/2 du. That 1/4 is still out in front. Or you could, if you want, you can distribute it, doesn't matter. So what we have to do here is we have 3/2 plus 1 over 3/2 plus 1 minus u 1/2 plus 1 over 1/2 plus 1. Now we do the algebra stuff. So it's going to be u 5/2 over 5/2 minus u 3/2 over 3/2. Take the denominators and reciprocate them. So that 5/2 becomes 2/5. 3/2 becomes 2/3. We can distribute. So we get 1/4 times 2/5 u to the 2 1/2 minus 1/4 times 2/3 times u 1 1/2. The 2 and the 4 cancel, the 2 and the 4 cancel. So we have 1/10 u squared square root of u 1/6 u square root of u. Now we put everything back in. So we replaced was 2x plus 1. So 2x plus 1 squared, square root of 2x plus 1 over 10. Two x plus 1 square root of 2x plus 1 over 6 plus c. Again, I don't know how the computer will take it. If it'll take this, this is with the simplified version. Or remember up here, we had 5 halves. I'm pretty sure you could have done the same thing. We could have had 2x plus 1 to the 5 halves over 10 minus 2x plus 1 to the 3 halves over 6 plus c. I don't know which one it wants. If we should leave it as an exponent, improper exponents, but in the true condition of math, the common conventions say always simplify. Never leave an improper fraction, never leave your exponent as improper fraction. So far so good. Getting a little bit easier. It's gonna take practice. Yeah, I'm not gonna lie to you, it's gonna take practice. So, but it's always the same procedure. First, once you find u and du, then it's if you have an extraneous x somewhere, then you have to solve for x. Example 7. We have 3 questions here. A, as sometimes we can use trigonometric identities to transform integrals we do not know to evaluate into ones we can evaluate. In other words, sine squared x dx. Do we know the integral of sine squared x? No. So using identity, how can we rewrite sine squared x using our trig identities? Typically, we don't want to have exponents in trig functions, unless it's a secant, because that's an easy tangent. But a lot of times when we have sine and cosines, that's going to be more difficult for us. One of the options here is this identity. It's on your cheat sheet. Because this is a lot easier to take an integral of than just anything exponentiated. So what we're doing here is we're going to take the integral of 1 minus cosine 2x over 2 dx. We have a constant fraction, so we get that out of there. Because remember what we did earlier? We can now take the integral of 1 dx minus the integral of cosine 2x dx. We can split them up. What's the integral of one? Hmm? Okay, yeah, because one is x to the 0 power. And if we integrate that, then we add one. So the integral of one is x to the first over one, which is just x. Now the integral of cosine 2x. Okay, let's look at this one. The integral, uh-oh. This one's tight. The integral of cosine 2x. How do you suggest we do that? Well, we don't know that. So what we can do is say that u is equal to 2x. Then du is 2 dx. So what does this one become? Cosine. Do we have a 2 dx? No, we need a 2 there, so we got to put a 1/2 out in front. The integral of cosine is sine u, which is 1/2 sine 2x. So far, so good. Any questions about this? All we did was substitute because we have a compound fraction. We have a trig function and an equation inside here. If it was just x, no problem, but it's an equation with 2x or 2x plus 5 or whatever. So we have to use substitution here. We're saying that that's u, and this is my du, but my du is missing a 2. So I got, it's not x squared, it's a 2 dx. So it's not an exponent, it's my coefficient of dx. All right, so this one becomes 1/2 sine 2x. Distribute, I got x over 2 minus sine 2x over 4 plus c. And there's your answer. Any questions about that? And that was A. Let's look at B. This is 7B. Integral of cosine squared x dx. From the equation. Yeah. I could just made it up, but it just looked good. Now, This one's pretty easy, actually. This is B. It's cosine squared x. We could do it two ways. One way, we know that from our sheet, cosine x is 1 plus cosine 2x over 2. Or we know that cosine squared x is 1 minus sine squared x. We just did sine squared x, didn't we? In other words, if we do this 1 minus sine squared x dx, actually, we'll do it both ways. We'll do the integral of 1 plus cosine 2x over 2. Sine squared x is 1 minus cosine x over 2. Move the 1/2 out in front. So it's x. The integral of 1 is x. Okay. Well, we could have done it. Or we could have done it the other way. If we could have done it this way, using this comparison. So cosine squared equals this. Take out the 1/2. Integral of 1 dx. Integral of cosine 2x dx. Integral of 1 is x. Integral cosine 2x, we just did that, was 1/2 sine 2x. So it's x over 2 plus sine 2x over 4 plus C. Since this one's a double angle, this is a single angle. So if we made that one a 2x, we'd have to multiply by 2. We get the same thing. The same equation. Yes.
First one, why is it x minus 1/2 and then it's like? I understand the 1/2, hold it forward from the cosine. And one
On this first one, yeah, because cosine, because it's cosine squared plus sine squared equals 1. So cosine squared equals 1 minus sine squared. So cosine squared is 1 minus. So now I take the integral of both of these. The integral of 1 minus the integral of sine. Okay, now the sine squared, we did that earlier with a double angle. It's 1 minus cosine. So that's why that one's a negative there.
Why is it x minus 1/2? No,
Oh, this one here?
yeah,
Because this 2, I take it out in front. And the bracket says I keep only the top part, 1 minus cosine x. This one, the integral of 1. This one, because we have 1 minus sine squared. The integral, I take integral of both of them. So the integral of 1 minus the integral of sine squared. Integral of 1 is x. Yes, because we have two equations. We have 1 minus sine, basically it's this. 1 minus sine squared x. This is 1 minus 1 minus cosine squared x. Or 1 minus cosine x over 2.
oh,
So you have the 2 ones there. And that's what one
that's because,
Yeah, very good questions. Very good questions. I mean, I did that pretty quick. I'm sorry, but yeah, that's
The other one, this one.
on this in front.
Oh, to the right.
This one? This one there. Yeah, when I finish 1/2 times 1/2 is 1/4.
Why is there 1/2? Isn't that 1/2? One.
The integral of cosine 2x is because, okay, what we did here. The integral of cosine 2x. U is 2x. Du is 2 dx. We're missing a 2 there. So we have to put a 2 in front of that dx. That means we have to divide by 1/2 in front. And that's why it became a 1/2 sine 2x. And that's where that one came from. Very good questions, actually. It's again, it's not the calculus that's going to hurt you, it's the algebra. Because in calculus, we'll go through all of the rules of algebra in one question, really. Okay, part C. The integral of tangent x. Oop, that should be dx instead of du. If you look at your sheet, what do you get? Which one? The integral of tangent is secant squared? Yeah, it's ln absolute value of x. I said, wow, that's secant squared is secant tangent tangents. Yeah, some weird equation. Now let's show you how you get that. Tangent is what in algebra, in trig form? So let's call this one U. What's the derivative of cosine? Negative sign. Dx. So what we have here now is U negative du. Because I need a negative up here, so I put a negative out in front. So the integral of du over u is what? Ln u. Du over u is the derivative of ln u. Ln u, integral of it is ln. So our answer is negative of ln u was cosine x plus c. Hold it. Okay. What does a negative in front of a logarithm mean? What do you do with it? What does this rule tell us? Whatever's in front of the ln can be written as the exponent of that ln. So what this gives us is ln cosine x to the negative 1. What is 1 over cosine? Yep. So it's ln absolute value of secant plus c. Simply because that negative becomes the exponent. Example 8. An integrand may require some algebraic manipulation before the substitution method is applied. For example, the integral of dx over e to the x plus e to the negative x. Oop, that's not dx. So we have our two functions here. So what do? Remember, the hint is we may need some algebraic manipulation. We can't split these up because they're on the denominator. If it was on top, it'd be easy. We do two separate ones, but we can't do anything there. So what do? We have a negative exponent down here. So how do we fix that? Oh, yes, the conjugate. Well, let's see. Okay. That might work. That might work. Let me hold for this one then. Let's look at your method. So if we multiplied both top and bottom by the conjugate, so e2x, those two cancel, minus e to the negative 2x. Nope, we still have it in there. Good try though, but it wouldn't happen. We still have a negative exponent. Well, let's get rid of the, how do you get rid of the fraction? Yeah. So since we do that to the bottom, we do that to also multiply top and bottom by e to the x, the common denominator. Ex dx. That becomes e2x plus 1. So far, so we don't have any more fractions, no more negative exponents. So now we have to do substitution. What is u? Which, how would you write this one? So we have u. What about that? So this would be u squared plus 1. But what's du? What's the derivative of e to the x? So this is du. So we have u squared plus 1 under du. If you look in your sheets, we'll look for this type of thing. Du u squared plus a squared. What would that equal? Y'all see that du over u squared plus a squared? One over a inverse tangent of u. U over a, yeah. Right. So in our equation, we know what u is. U is e to the x. What is a? 1. So this one becomes 1 over 1 inverse tangent of e to the x over 1, which is tangent inverse. There's our answer. Yeah, so basically, you don't want to have fractions within fractions. You don't want to have any negative exponents. Okay. Let's look at this one. Now go to the next page. B. Integral of secant x dx. This one's not so readily acceptable, or not acceptable, let's say noticeable. So what you have to look for here, what integrals do we have that has secant either as an individual term or as a fraction? Look. So what does it look like? Remember, we want this to be a derivative. Whose derivative is some function of secant? Look at this one. Whose derivative is that? Hmm? Why do we want secant and tangent together? Common denominators. Secant is 1 over cosine, tangent is sine over cosine. So what we do here, again, as I said, this is not readily observable. If we multiply it by 1, so we need something, so we need a fraction. If we multiply those two together, what happens? See, here's where we're trying to force the derivative of u du. So if we multiply these together, we get secant squared x plus secant tangent x over secant x plus tangent x. Let's say that u is secant x plus tangent x. What's du? What's the derivative of secant? Plus, what's the derivative of tangent? Look familiar? The derivative of secant plus tangent is secant tangent plus secant squared. So what we have here is du over u. What is the integral of du over u equal? Yeah, that 8B was not that easy because you can go through a whole bunch of different things and see what happens. So what we're looking for is we're trying to set it up to be in this format, du over u. The reason being because the integral of du over u is the ln of the absolute value of u. The integral of du over u is ln u plus c. Or the derivative of ln u is du over u. So that's ln absolute value of secant x plus tangent x plus c. Why do we put absolute values around the secant x plus tangent x? Because you cannot take logarithms of negative numbers or zero. So what we have to do here is make sure because secant and tangent could both be negative values. So we want the absolute value only. So that's where we take the absolute value of it. Integrals of those. So the integral of tangent x dx is equal to the ln of secant x. The integral of cotangent dx is the ln of the sine function. Is the ln of secant x plus tangent x plus c. And the cosecant is the negative ln of cosecant minus cotangent. Yeah, if we had had these earlier, it would have made it much easier for us. But you had them on your sheet. You have to meet the problem of having that cheat sheet is you have to go through so many of them. And so I would, the ones you don't normally use, I would put a mark next to them or highlight them so it's much faster. So these are the shortcuts. All right, let's look at example number 9. The integral of 2x dx over the cube root of x squared plus 1. This example is one, as we said earlier, to do these things is not that easy because you have so many options to choose from. Which one do you choose? There is no set rule. It comes with practice. So just try one. If it works, Great. If it doesn't work, guess what? Try another one. And that doesn't sound too mathematical, but again, there is no magic bullet for here. It's just whatever works. Like that last example, secant plus tangent over secant plus tangent, that equals 1. Whoever thought? The reason you put those together is because we can see that the derivative of secant is secant squared, or tangent secant, and derivative of tangent is secant tangent, or secant squared. So it's just, it comes with practice and trial and error. With this one, what would you do first? Right. Steps. Step 1, stare at it. You're gonna write that down. Oh yeah, I just said it there. So we have to first find, we're gonna use substitution. So we have to first find u. Which one's gonna be u? The top or the bottom? And what part of the bottom? Yeah. The reason we will choose that one, because when you find du is 2x dx. Well, that's what the top is already. So what this becomes, since we have the top is already 2x dx, that's du. And on the bottom, we have the cube root of u. Now we're going to manipulate it algebraically. What's the next step? Rewrite the radical as an exponent. So it's u to the power 1/3. Since there's no other u inside there, we have u to the power negative 1/3 du. Now integrate it. So it's u negative 1/3 plus 1 over negative 1/3 plus 1 plus c. So that's 3/3, so it's 2/3 over 2/3. Reciprocate the bottom. And then substitute it back in there. U was x squared plus 1. Which could be rewritten as the cube root of x squared plus 1 squared over 2 plus c. Either one of these would work in my book. What do y'all think? Okay, that's the end of that section.